So you should have just been looking at this image on the Jamboard. And what you probably noticed is that if we look at the group 4 with the methane, silicon, germanium, and tin, what we see is that there's a nice increase in the boiling point for each of those compounds as we go down the periodic table, which is in line presumably with what you've noticed as we are looking at the impact of molecular weight. And that holds true if we look at group 5, group 6, or 7, right? As we go down the periodic table, what we see is that the molecular weight or the boiling point increases as the molecular weight increases. But you probably notice that these three are kind of out of place. They're not really fitting the trend. And that's what we want to talk about just a little bit here. We actually have another kind of intermolecular force. That's our hydrogen bonding interactions. One of the things I'll say is this is the worst name in chemistry ever, basically, that it's not really a bond, but we call it hydrogen bonding anyways. Very frustrating. It's really just a subset of our dipole-dipole interactions, though. But they tend to be the strongest of the dipole-dipole interactions, enough so that we actually sort of set them apart and give them their own name because they have enough impact on the properties of molecules. They occur when we have a really large delta plus interacting with a really large delta minus. And that's usually on a lone pair. And so what we have here is representation of water interacting with itself, and these intermolecular forces that we have here and the blue dots are our hydrogen bonding. Again, that subset of dipole-dipole. So don't feel like we've misled you along the way when we've been referring to it in that context. But again, we also see that it happens with HF and NH3. And the reasons that it happens with these molecules in particular, these atoms in particular, is because we have really polar bonds that exist between these most electronegative atoms, the hydrogen, nitrogen, and oxygen, and the hydrogen, as well as the fact that the fluorine, nitrogen, and oxygen are relatively small. And because they're small, that charge is relatively localized, so we get particularly large delta minuses on those. Now, again, our hydrogen bonding interactions, I want to stress, these are really between two different molecules. And so when we look at it, we'll have something attached to hydrogen, and it's the interaction here over to that other molecule, where X is always going to be an oxygen, nitrogen, or fluorine. So that's the interaction that we're looking for between those molecules. So that's what's depicted over here or down here. And hydrogen bonding, again, it's an extremely strong kind of dipole-dipole interaction, again, enough so that we give it its own name. And what we see is that compounds with hydrogen bonding interactions, keep in mind they also have dipole-dipole, and they also have LDF, so it's not just a single kind of force that they have. But often there's a little bit of a cascade. Again, if we have these really strong enough dipoles to be able to form hydrogen bonding, there usually are other pluses and minuses as well. And then because we have the electrons, we always have London dispersion forces that can exist. There are a number of examples that have it. We've cited obviously the ones just between the elements and oxygen and hydrogen, but methanol right here or ethanol, those are all other examples that also have this hydrogen bonding as well, because we still have that OH bond. And that hydrogen has a really big delta plus, so it can be attracted to the oxygen on another molecule, which would have a strong delta minus. And so we can still have that kind of intermolecular force that exists there. And as you're working on this, you should just be aware that you ought to be able to draw the Lewis structure for these compounds, identify the polarity, and then draw the hydrogen bonding interactions between the molecules if you need to. So you should be able to draw something like this, for example, to represent hydrogen bonding.